When we talk about mapping, what is it we really mean? What is a map in the broadest sense? Are they, as J.B. Hartley says, quote, mediators between an inner mental world and an outer physical world, helping the human mind make sense of its universe at various scales, employed as literary metaphors and as tools in analogical thinking, end quote. Do they, quote, constitute a specialized graphic language, an instrument of communication that has influenced behavioral characteristics and the social life of humanity, end quote. Is the Harvard Guide to American History giving us a full enough picture when it says maps, quote, constitute a common language used by men of different races and tongues to express the relationship of their society to a geographic environment, end quote. Or do the words from the preface of the University of Wisconsin's hugely ambitious and important history of cartography say, quote, as visual embodiments of these various conceptions of space, maps have deepened and expanded the consciousness of many societies. They are the primary medium for transmitting ideas and knowledge about space. As enduring works of graphic synthesis, they can play a more important role in history than do their makers. In this sense, their significance transcends their artifactual value. As images, they evoke complex meanings and responses, and thus record more than factual information on particular events and places. Viewed in such a light, as a focus for social and cultural history, the history of cartography can be placed in its proper context, an essential part of a much wider humanistic endeavor, end quote. Does that capture the full essence of what a map is? There is, of course, the typical thing that comes to mind when one mentions the word map, a picture, often drawn through either human or nowadays electronic means on some medium that incorporates culturally relevant symbology to give a sense of something's place in space. However, when you poke around a bit more at the idea of how we use the word in our language, that idea becomes so much richer. In neuroscience, it is common to talk about mapping the brain or the activity in the brain as a way of locating the areas where neural function is heightened during certain types of cognitive or sensory functions, leading to ephemeral impressions arising or emerging out of shared individual neuron activation. Mathematicians will talk about functions that quote-unquote map one thing, one set of numbers or perhaps abstract numerical concepts into or onto other numbers or numerical concepts. In educational pedagogy, one of the best ways to get a student to learn a group of related ideas is to have them draw something called a concept map, where ideas are represented by terms that are connected by ideas represented through action words. As we have mentioned in previous episodes, maps have long been associated with the descriptions and discussions of the sacred, both spaces and ideas, representing associations between the physical and metaphysical in ways that are often metaphorical or allegorical. A great question I've always heard is the biblical story or parable of the rich man and Lazarus, as related in Luke's account of the gospel, to be taken as a real description of the space separating the two after death, or does it represent a spiritual or metaphysical state? When we allow ourselves to think beyond the artifact of a chart, or carta in Latin, a map becomes something more than just the physical. A map becomes that thing, whatever it might be, that connects and expands while also positioning and placing. In fact, what might be the most powerful thing in mapping writ broadly is the way in which maps connect. For it is in those connections, I think, that the true power of a map is realized. Let's think about this perhaps in a very simple way. Yes, I may know that there's a place where I live, here in a small town in central Georgia. And yes, I may know that there's a place called Atlanta. But those two pieces of knowledge are limited in so many ways. It is only when I begin to construct a spatial relationship between the two, a connection, that those two pieces of information begin to have any real relevance, at least with respect to each other. It is only in knowing that Atlanta is north of my little town by some 20 or so leagues, and that both municipal entities are within a larger political unit known as the state of Georgia, not to be confused with the nation of Georgia, that such relevance begins to emerge. Furthermore, if I tell you that my town is the capital of the county Lamar, while Atlanta is both the capital of the state and the location of the Capitol building of the state, and is thus where many of the governing decisions that might affect the city in which I live takes place, then you now know even more. It is in these connections, in the relationships that they sort of enlighten, that the fuller, richer, and more valuable picture emerges or takes place. But as you may have noticed in that previous description, there is something that you and I have to share for that relevance to be fully appreciated and understood. We both have to know what north represents, and that the locations I'm talking about are in the northern hemisphere of our world. You have to know what a league is. Perhaps you remember it from our last episode, the distance a typical person can walk across level ground in an hour. And by the way, that definition gives one a whole new sense of the fantasticalness of Jules Verne's famous science fiction story, 20,000 Leagues Under the Sea, wherein the voyage underwater is over a distance a man might walk in a bit more than 55 years, more than twice the circumference of the Earth. Getting back to our example, you would have to also know that in English there is a difference between a capital, the seat of government for a political entity, and a capitol, the building in which a legislative or ruling body meets. You would need to know the difference between the geographical and political divisions of a county, a state, at least a state as a part of a republic as opposed to a word synonymous with nation, and a nation. For me to communicate with you the relationship and connection of my small town or city and the much larger metropolis of Atlanta, there's a lot we have to have in common, the kind of stuff that goes into making culture. One of the things I've heard said is that for one to truly understand a culture, one must know that culture's language. And for one to truly understand a language, one must have a sense of the culture that language arose in. I've heard chicken and egg sorts of arguments about this as to which came first, but what really seems to me to be clear is that they probably evolved together in a synthesis and with a synergy. What also may be said, however, is that language acts as a map of culture. That's the thing I'd like to take some time to explore in this episode of the show. If language can be said to act in some ways as a cultural mapping tool, how does that language affect mapping and how we interpret maps from the past? Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 5, Finding Our Way. Episode 4, Emerging from Connections. When you look at a map today, it's easy, I think, to just sort of pass over what a remarkable thing that map really is. And of course, what I mean by map here is pretty much what all of you thought when I said map. A document of some kind that showed the spatial relationship between a number of things. Maybe it's a paper map like the kind you used to buy in a gas station convenience store, or what I used to breathlessly await when that month's National Geographic came, or, more likely these days, the picture your phone gives you when you pull up your preferred mapping app so that you can determine the best way to get from one place to another. What's remarkable about it is that it's so commonplace in many ways, and yet there's so much that goes into that kind of a representation on so many levels. For example, one of the things I spend some time talking about with my students, and that I shared with you all in the first season of this podcast, was the idea that in science we will often use models. Things that represent a physical system, usually simplifying the system to emphasize certain key features in a way that often changes the size or scale of that system. A map, I think, is a great example of a model. Another really cool thing is that a map is a physical technology that captures an abstract mental process. Think of it as a bit like a writing system, actually. Any writing system is a physical expression of a language, which itself is a technology or set of tools that extends innate human capacity. In this case, something that allows for the communication of ideas. Just like language, and the writing that has followed it in so many cultures, developing spatial concepts that can be communicated and then represented is a complex activity that evolves and changes over the time. Well, I'll leave it for linguists to talk much more capably than I can about the topics of the evolution of language and writing. From what I've read and learned over the years, it's clear that both of these things have developed over time and in response to cultural needs and pressure. Writing, for example, has been shown in some cultures to begin as representative pictures, where an image is associated with a concrete thing, such as two repeated triangles with the pointy ends being up, and that represents tents or huts becoming a symbol for a dwelling place in the language. This is associated with an already existing word for that same idea, say bet or beth, to mean dwelling place. In more complex words, perhaps the simple compound words we all learned in grade school, or in even something more nuanced that involves the joining of concepts, the symbols are combined either linearly, as was often the case in some hieroglyphic writing systems, or layered, as was sometimes the case in Asian systems. Over time, as the writing system became unwieldy due to the overwhelming number of things that are symbolized, the pictures began to represent syllables in words, and then sounds, what might be called phonemes. As this process took place, the drawing of the picture was abstracted to become simpler and easier to produce, and so it was that the picture of multiple tents or huts comes to represent the B sound, while also being turned on its side in many written languages. So it is that the technology of writing comes into being, evolves, and becomes to a degree abstracted and simplified. And, as a note here, my apologies to all of our crew who love language and who are no doubt feeling a bit twitchy about my startling oversimplification of what was a millennia-long process in most cultures that developed writing. If I got anything really out of whack in that brief description, send me a note educating me, and I'll make the appropriate corrections in a later episode. There's a similar process going on with maps. They are a technology that has been developed to extend human capacity, and they do this through encoding information. Like language, maps started off as something much rougher, much less information dense, and then evolved to become more efficient as a society's needs dictated. They were, and remain, a shorthand and visual way to communicate information. Like language, maps started out as pictures, and while they, by and large, have remained as such, the way in which information has been encoded pictorially has changed over time, often, much like language, becoming more abstract. Take elevation, for example. Many historians of cartography suggest that very early map makers accounted for topography by warping their maps in ways that retained spatial relationships, but that sacrificed linearity by drawing what might have been straight lines for paths or property boundaries as curves as they went over hills or through gullies or hollows in a way that would have been similar to what one might have seen if one climbed to a nearby high point to observe a small village. In modern-day maps, however, a new way of representing elevation has evolved. The roads and boundaries are drawn as straight lines when appropriate on two-dimensional surfaces, and the changes in elevation are now represented by contour lines, a change made useful by the adoption of globally based coordinate systems, something our ancient map makers would never have considered. Another example of this involves a congruence between the evolution of the idea of direction and the development of its symbolic representation in writing. As we mentioned in the early episodes in our series on the history of finding our place in the universe, a good bit of telling direction in many cultures comes from observing celestial phenomena. The most consequential of these, of course, is the rising and setting of the sun on the eastern and western horizons, respectively. These astronomical events define space in a somewhat absolute way in many cultures. In Latin, oriens is a word associated with the rising of the sun and thus came to mean east. Occidens is associated with the sun setting and thus means west. This is true for many languages that derive from a very early root language known as Proto-Indo-European. According to dictionary.com, in Sanskrit, for example, the word for dawn or morning is yusas, which is related to the word for east, while the word for west, avha, literally means to go down. The name of Japan in Chinese is Nippon or Nihon, which literally translates as the land of the rising sun, or, just straightforwardly, the land to the east. Additionally, in one of the Chinese character sets, the symbol for east, known as dong, is a superposition of two other symbols, that of the sun, or ri, and the one for tree, or mu. This superposition is clearly a pictogram for the sun rising behind a tree on the horizon, and thus comes to represent east. This extends to north and south as well. If you face the rising sun to the east, north will be on your left. In a number of Indo-European languages, the word for north, or nord, is thought by some linguists to be derived from the Proto-Indo-European word for left, or ner. Interestingly, this word can also mean below, hinting at an association with the root word for night. In Hungarian, the word for north, észak, is derived from the word for night, éjszaka. In other languages, the word for north is derived from the name for the various astronomical asterisms, or constellations, associated with the 7 circumpolar stars that circle the North Star, what we commonly call the Big Dipper in the United States and Canada. In Greek, one of the words for north is Arctus, which derives from the Proto-Indo-European Herktos, which means bear. This, of course, relates to the fact that the Greeks, instead of seeing a Big Dipper, saw a great bear as sort of being represented in those 7 stars. In Latin, the word north is septentriones, which is literally 7 oxen, referring to the stars as 7 oxen that pull a plow, which the Big Dipper can also look like. Direction names can also be derived from geographic or climatological information. In ancient Egyptian, the words for north and south are related to upstream and downstream, owing to the Nile River's centrality in that culture. In Old Norse, the words for north and south are what you might expect, norður and suður. But the intermediate points of the directional compass had to do with whether a ship was sailing towards or away from the main land mass of Scandinavia. Northeast was actually, or is actually, landnorður, or literally land north, as a ship sailing in that direction in the North Atlantic would be traveling north and towards land. Southwest would be utsuður, or away south. Another example of this sort of thing comes from winds and their characteristics, which can lend their names to directions as well. Another Greek word for north, boreas, comes from the name of the cold, dry wind that blows from that direction. The Native American Tuscarora tribes of the coastal Carolinas had, like the Norse did, an 8 cardinal point system, but rather than those 8 points being defined by the co-equal astronomical and geographic bearings, they were named for 8 unique wind directions, each with its own climatological conditions, as reported by the British surveyor we mentioned in our last episode, John Lawson. As a final closing note on this topic that relates back to our previous episode, one of the things I learned in my researches for this show was a possible origin for the version of something known as a compass rose. One version of this is a diagram where the direction on a map is represented in a way that sort of has 32 spikes around a circle. The cardinal directions, of course, account for 4 of these. The points made by dividing the angles between these cardinal points in halves, what we would call northeast, southeast, southwest, and northwest, account for another 4. These, in turn, can be divided again into the somewhat less familiar, but not uncommon, north, northwest, and associated terms to give a 16-fold division. Finally, in some versions of the compass rose, usually associated with nautical context, one will see an additional division of these into a total of 32 pointings. The reason for this is really twofold. First, when the compass was first coming into use in medieval Europe, the state of mathematics there was pretty limited. While the scholars of the scholastic universities might have known about a degree-based measurement system for a circle, that knowledge didn't always transfer over to ship's navigators. Thus, the easier method was to go through a process of successive bisections of the angles, beginning with the cardinal directions, until a fine enough scale was reached for the navigational tools of the time. These 16 or 32-fold divisions of the circle were then drawn or printed onto a backing card for a compass that the needle of the instrument could then be compared to. Since these printings often were done with an artistic flourish that represented the subdivisions as something like the opening of the petals of a flower, these images would become known as a compass rose, and they would allow the navigator to quickly sight the orientation of the compass needle for navigational purposes. Another reason, however, for all of this goes back to that practice of using one's hand to measure angle. If you divide 360 degrees by 32, you'll get 11.25 degrees per smallest subdivision, which corresponds pretty well to the angle the fist makes when held at arm's length. So what that means is, if you can sight the North Star down to the horizon, and you call that 0 degrees, for example, each fist's width around the horizon will represent roughly one of those 32 subdivisions, which makes that a useful method to dead reckon by at sea or when traveling across relatively featureless landscapes, especially before the time of compasses. This measurement around the horizon was and is still known as determining an object's azimuth, or direction's azimuth, a word derived from the Arabic asumut, which means the ways. In nautical communities, as opposed to astronomical ones, it is still common for a direction to be given in one of the names from the compass rose, i.e. west by northwest, something that you'll see in a good, authentic telling of a nautical tale. One of the most interesting and compelling accounts of navigation using the sun in its rising and setting can be found in what are known as the Finland Sagas, which consist of two works, the Saga of the Greenlanders and the Saga of Eric the Red. And by the way, what's really great about these things is what we'll see here as we talk about this is this interrelationship, these connections between how the thinking about direction in space get related in the language of the Norse people and also in what they actually physically do to the landscape around them to create sort of images of those maps. So these tales recount the discovery of new lands found across the sea to the west from Iceland, which is where a community of Norse seafarers had settled. And in the words of the sagas, one can learn a bit about how to use solar observations that allowed these brave souls to develop first route knowledge to navigate the North Atlantic, and then something approaching survey knowledge that would allow them to quote-unquote discover the North American continent, explore its coast, possibly as far south as New York State, and even establish a short-lived colony on its shores some 5 centuries before Columbus sailed the ocean blue. The key idea for understanding how this was done is to see within the saga how the Norse sailors used the sun to tell time, and they used the length of the day to reckon both direction of travel and relative latitude compared to their home ports. Now, as many of you know, the coast of Norway is at what is known as a high latitude, and that means that it's a good bit further from the planet's equator and closer to one of the poles, in this case, the North Pole. In the case of Narvik, a port that might have been used during the time of the sagas, the latitude is actually about 68 degrees north. This puts the port just slightly north of the Arctic Circle, which means that due to the tilt of the Earth on its axis, on a few days near the summer solstice, or June 21st, the sun never actually quite sets on the horizon. Instead, it just grazes the northern horizon in the hours just on either side of midnight before swinging first through the eastern sky and then to the south, rising somewhat higher altitudes as the day goes on. Conversely, of course, near the time of the winter solstice, December 21st, the sun never quite rises, only creating a dawn-like glow on the southern horizon for a few hours around noon. And, as an aside, if you're wondering what on earth anyone that far north and cold, at least in our terms today, would be doing going around and sailing the precarious seas of the North Atlantic, what you should know about this period of time, this, time frame around 1000 CE, maybe for 200 years before and 150 to 200 years after, the continent of Europe was in the middle of what is now known by historians as the Little Optimum. The little optimum is where temperatures were as much as 2 or 3 degrees Celsius above the recent historical mean temperatures of the time. This allowed for the cultivation of more land, higher birth rates, and pressure for young adventurers to seek their fortunes away from the increasingly crowded places that had served families for several centuries. It also opened up the seas to more hospitable conditions for longer periods, thus allowing for more audacious voyages to discover new places, including Iceland, Greenland, and Vinland, as North America would be called, due to the abundance of wild grapevines the adventurers found on its shores. Okay, so back to using sunrise and sunset to navigate by. At the 2 equinoxes, of course, the sun will rise due east and set due west everywhere on the planet. It's something we talked about in our History of Astronomy series in those early episodes. In the northern hemisphere, in the period from the spring or vernal equinox to the summer solstice, the sun will rise further and further north of east at a given latitude until about June 21st or so. And on that date it will rise as far north on the horizon as it will for the entire year. Now, how far north that was or is depends on the latitude that you're at, with the angle north of east increasing the further north you are until you reach that 67.5 degrees north latitude, above which, as we've mentioned, the sun will actually not rise or set, but instead travel in sort of a circle around the sky above the horizon. What this also means is that the further north you go, the longer the length of the days will be in the summer. Where I live here in Georgia, the length of the days at the summer solstice is a bit more than 14 hours. When I lived a bit further north, or at a higher latitude in Kansas, the length of those days approached 15 hours, and in Oregon, where I was born and raised, the summer days were about 15 and a half hours long. Again, near the winter solstice, the converse is true. The sun rises further south of east, sets further south of west, and so the days are shorter. As a kid growing up, I can remember the sun coming up at around 8 a.m. and being close to setting at about 4:30 p.m., only about 8.5 hours of sunlight. In a place like Edinburgh, Scotland, the sun is above the horizon a scant 5.5 hours on Christmas Day. In Iceland, it's only 3. Now, if you're a Norseman and you live in a place further up the Norwegian coast, or maybe in Iceland as we talked about, or even north of that in Greenland, there's something really interesting that you can do. Since the sun near the summer solstice will travel around the horizon, either always above it or almost above it, in the case of Iceland, the direction that the sun's actually at actually acts like a clock. At midnight, or midniete in Old Norse, the sun will sit above due north. 3 hours later, known as Ota, it will be a bit higher in the sky above northeast. 3 hours after that, it will be due east at Midmorgen, or mid-morning, which would correspond to our 6 or so a.m. 9 a.m. would be dagmal, or daymeal, and the sun would be southeast, a bit higher up, and at high noon, or hagedi, high day, it would be at due south. So it would be that the Norse would divide their days up into 8 roughly equal parts that corresponded with those first subdivisions of the cardinal directions. Once a person recognized this, it would be easy to assign horizon landmarks, say a rock outcropping or building or even trees at various times, to mark if the sun is above that thing, it's this time of day. These were, and still are, known as dagsmark, or day marks, and they're, like I say, still used today. In fact, one visitor to Iceland in the 1800s wrote, quote, "This mountain forms the meridian day mark of the Grimstad family. Few of the Icelanders being in possession of watches, the only sundial they make use of is the natural horizon, which they divide into 8 equal points, called day marks, availing themselves of certain peaks or projections of the mountains, or, in absence of these, they erect pyramids of stones of corresponding heights. Most of these kinds of pyramids have originally been raised by the first settlers from Norway, and have been held in repair for generation to generation, which circumstance will count for the difference of time between Icelandic computation and that in common use with us." End quote. Note that from the quote, we have the sense that this practice dates back to the first Norse settlements on Iceland, those dating to over 1,000 years ago, a practice the next generation of explorers, including Eric the Red, Leif Erikson, and his brothers Thorvald and Thorson, would certainly have used as they traveled first to Greenland and then down the coast of North America. These markers, called stad, were therefore associated not just with a time of day or a direction, but with both, and so their names would become conflated, with the southward marker, for example, being called Hadegastad. When one travels to Iceland today, you can find places with the names such as Midmorgenshinkur, or Mid-Morning Peak, or Dagmalahol, meaning Daymark Hill. When Leif Erikson explores what he calls Vinland, the saga makes reference to the path of the sun through the winter sky. In translation, it reads something like, "The days and nights were much more equal in length than in Greenland or Iceland. On the short days, the sun passed Ektarstad and Dagmalstad." Another way to say this is that in the middle of winter, the sun passed the Ekit point, or southeast, and the Dagmal point, or southwest. Given that the angle between these points on the horizon is 90 degrees, that gives the reader the indication that the sun was above the horizon for somewhere around 6 hours near the winter solstice, something that wouldn't have happened at Nordic settlements in Iceland or Greenland. This tells us that the adventurers had to be a good bit south along the North American eastern coastline, a historical account that is consistent with the ruins from a Norse settlement found at Lands Oxmeadows in present-day Newfoundland. In this way, the sun's position acted as a timekeeping device for people used to long days and nights near the solstice. Of course, a similar method of keeping time would be to use the shadow cast by a stick, and in northern Europe, the liturgical hours of the day would be kept by observing the position of a shadow cast on the wall of a local church, with each 3 hours past being noted by the ringing of a bell calling the faithful to worship. Similarly, there is the tradition in Islam of the call to mid-afternoon prayer being signaled by the length of a shadow cast. Here again, as we mentioned in the last episode, tracing the path of the end of a shadow cast by a gnomon or an upright stick can be used to determine the direction of the sun. A path traced on one day with the shortest length of shadow indicating when the sun is due south can be used for as much as a week's time with the gnomon placed on the marker and the paper rotated until the shadow meets an originally traced line. Such a method was used by Allied troops during the North African campaign in World War II. Due to the magnetic nature of steel used to build the motorized cavalry vehicles such as jeeps and Sherman tanks, compasses were often unreliable due to the interference from the iron in that steel. The Sum Compass, as it was called, that we just described, allowed the troops to navigate the vast expanses of the Sahara with surprising accuracy once the technique was mastered. There is even evidence that such a device may have been used by the same Norse explorers we've been talking about to help them navigate across the sometimes featureless expanses of Greenland. To conclude this section, let me tell you what I think may be one of the most ingenious ways I've ever heard of to use the sun to determine direction, that of the sunstone. Now, if you spend much time outdoors and you pay attention just a bit, you begin to recognize that the quality of light coming from the sky changes throughout the day, and it can vary from day to day. For example, here in the southeastern part of the United States, on days when the humidity is high, the sky is a much paler blue on clear days, while in the fall, when the humidity drops, the blue becomes much deeper and richer. This has to do with the presence of water vapor in the air. To understand this, you have to understand that light coming from the sun is made up of all colors in the visible spectrum, from blue light on the one end of the spectrum to red light on the other, at least the visible part of that spectrum. The nitrogen in the Earth's atmosphere, making up roughly 4 to 5 parts, tends to scatter the blue light with shorter wavelengths more readily than it does the red light, which has longer wavelengths. The reason the sky looks blue on a clear day is that you are seeing more blue light scattered from other parts of the sky than you do red light, and so that dominates what you see. In the morning and evening, at sunrise and sunset, the more of that blue light is scattered out of your line of sight, so that other people get to see a blue sky, and so the sky looks yellow, orange, and red during those times, giving rise, of course, to those glorious sunsets. Water vapor, with its larger molecular size, scatters the different colors more equally, which causes the sky to look whiter or paler. This is why clouds, being primarily made of water vapor, look white. The other thing that this scattering does is it polarizes the light, meaning that the crests and troughs of the light waves all end up oriented in the same directions. Now, when the sun is high in the sky, this polarization tends to be parallel to the horizon, while when the sun is near the horizon, it tends to be perpendicular. When in fact, one of the techniques of a good photographer is to understand this and use a polarizing filter to achieve more dramatic results, especially when shooting in black and white. If you're a fan of Ansel Adams' work, he was a master of this. Now, it's the second piece of information that's going to turn out to be really relevant for our discussion. When the sun is closest to the horizon, it is the light coming directly overhead that is most polarized, and that polarization will be perpendicular to where the sun is near the horizon. For example, if the sun is rising near due east, as would be the case near an equinox, the polarization direction of the light coming from directly above you would be along a north-south line. As an aside, it's been shown that with certain species of ants, that they have structures in their eyes that can actually detect this polarization direction and are thus able to use it to determine direction and thus navigate. For human beings to do the same thing, we have to use a tool, as our eyes don't have those similar kinds of structures. Fortunately, there are certain types of minerals that form large crystals that will actually do it for us. The most common of these is a mineral known as calcium carbonate, or calcite, or Icelandic spar, due to its being found in large quantities in the form of large single crystals on the east side of the island. A good way to visualize one of these crystals is to think of sort of a block that's wider and taller than it is thick in the shape of a rhombus. One feature of this crystal is that it displays a property known as birefringence, wherein it bends light passing through it differently depending on how that light's polarized. So here's where we bring this all together. In a Norse saga known as Finland Saga, there is a section that reads, quote, "The weather was dark and stormy. The king looked about and saw no blue sky. The king took out the sunstone and held it up, and he saw where the sun beamed from the stone." End quote. Author, sailor, and investigator Leif Carlson has taken this passage and worked out how a large crystal of calcite would be able to determine the direction of the sun, even if it was hidden from sight by clouds or fogs, as would have been common for a sailor. What he showed that if one puts a small dollop or a little bit of pine pitch on the crystal spar, the blue light from the sky will normally give two images of that spot when you try to view it through the other side of the crystal, due to the fact that that blue light that's being reflected off that spot is differently polarized coming from different parts of the sky. However, when you rotate the spar kind of around its middles, what will happen is that one of those images will disappear when the spar is perpendicular to the dominant polarization direction. This means that the long axis of the crystal will now point pretty closely in the direction of the sun, especially if the sun is near the horizon. Author and teacher John Huth has had his students test Carlson's technique and found that it worked within 5 or so degrees of determining the sun's position. Now, I don't know about you, but I think it's pretty wild and really cool to imagine a ship sailing out in the North Atlantic, and it sort of, sails into this fog bank early in the morning. The crew can't see the sun to get a directional fix, but they can see the sky overhead. And, for any of you that have spent some time out on the water, you kind of know how common this sort of thing is, especially on days where the water is warmer than the air. You tend to get this fog bank sort of near the horizon that obscures everything, but if you look straight up, you can actually see blue sky. So, you get this kind of a situation and nobody knows what direction is what because fog is super, super disorienting. And so what happens is the ship's captain or navigator pulls out this, what must have seemed like this magical stone, the sunstone, and then, goes through this intricate sort of looking ritual that you don't really understand, and then holds the sun over his head and looks through it, and just by looking upward through the stone at the sky is able to find the hidden sun and thus give you a good directional fix to work from. And in addition to that, since, as we talked about, direction and time are related, it also gives you a good sense of time. From that would allow you to work out your latitude. I think that's all just really amazing when you come to think about it. As I hope you can see, the navigational concepts we've been talking about over the last 2 episodes are tied intricately with other deep and fundamental cultural concepts, things like language and time. As these connections are worked out and spatial models develop, they are then encoded, first in saga and song, and then, in time, to physical artifacts. One of the enduring mysteries of the Finland Sagas is just what the various lands Leif Erikson is said to have visited were. What we have are a few written descriptions of what the space might have looked like in a crude physical map, but they're not accurate enough to draw any firm conclusions about what specific routes were taken or where any settlements besides the one in Newfoundland may have been located. And this, I think, shows us where it is that a map begins to transcend the things it's connected to, where it is more than art or a figurative description of conceptual associations. While songs and stories can relate route knowledge, it is a physical map that can give that most important of pictures, the survey knowledge that allows a traveler to not just follow in another's footsteps, but to find their own way. In our next episode of the Scientific Odyssey, we'll begin our journey through the history of cartography by looking at the earliest good examples of things we know to be maps and seeing what they tell us about the human search for a greater understanding of the world they encountered. As we wrap up, let me, as always, give a big thanks to the Blue Dot Sessions for allowing us to use their compositions to provide an oral landscape of our considerations. You can find more of their work by searching on their name or by going to sessions.blue. If you're interested in connecting with the crew and our voyage, join our Facebook group. You just have to search on our name out there at Facebook and you'll find us very easily. You can also follow me, your humble navigator, on Twitter, @ChadDavies, or on Instagram, where I go by Odyssey Navigator. Or finally, it'd be really great if you wanted to go out and, if you use Reddit, join our Reddit group, just known as the Scientific Odyssey. You can leave comments about the show, ask questions, or share your most recent scientific adventures. I know that everyone would love to hear from you and see what you're up to. So hopefully you can find time to connect with us out there. Until next time, full sails on your journey.